Hello, this is Mr. Huber. In this lesson, we're going to learn about lines of best fit. If we recall, a y equals mx plus b slope-intercept form, our most common way that we write an equation of a line, is a line that tells us the slope and y-intercept, and all of the points that are on this graph are points that are solutions for the equation. Well, not everything always fits on an exact line. We can see here some points here that wouldn't be a straight line going through all of them. That's called a scatter plot, where the points are more scattered around on the coordinate plane. So when we have a scatter plot, we could see trends in the data. So when we have scatter plots here, we might have points that all generally go up from left to right or down from left to right. This is a positive correlation. Correlation is the name we give to how those data are correlated with one another, how related to each other. Here, as the x increases, the y also increases. Here, as the x decreases, the y also decreases. This line here would be the line that best fits through the data, right? This would have a positive slope. This line would have a negative slope. This is called a positive correlation. When x increases, y increases. A negative correlation, that would generally have a negative slope to it. As x increases, the y decreases. And when there's no correlation, the points really are scattered around, and we don't see there's any trend in as x increases, the y is going up or down. They really are scattered all over the place. So positive correlation, negative correlation, no correlation. So let's practice describing the correlation in the data in these graphs below. So here we have data generally going up to the right. This would be considered a positive correlation. As x increases, the y increases, or in this case, as hours studying increase, test scores increase. Okay? Right? So we can put labels on those here. We always start with as the x is increasing. So as hours studying increases, the test scores are also increasing. That's a positive correlation, right? There would be a positive slope of a line going through a line of best fit there. Okay? Now in this next one, this would have a negative correlation, right? This would be a negative correlation because as hours of TV increase, right, as the x increases, I always start with as what's happening with the x increases. So as hours of television increase, test scores decrease. Right? The y value decreases. So as x increases, y decreases. That's a negative correlation. We always start with as whatever's on the x-axis increases. So as hours studying increase, what happens to the y value? As hours of television increases, what happens to the y value? Right? So as hours studying increase, test scores increase. As hours TV increase, test scores decrease. Positive correlation, negative correlation. When the data have a positive or negative correlation, the trend can be modeled by a line of best fit. That's a line that we draw as best we can through the points, even though it's not going to be an exact line that touches all of the points. We want a line that has about as many points above and below, so basically goes through the middle of the data, and then we can pick 2 points on the line. They don't have to be 2 points from our data set, just any 2 points that are on that line of fit that we drew, and we can write an equation for that by finding the slope, using a point, and getting a slope-intercept form equation written. So let's practice that here. First, we're going to draw the scatter plot, and then we're going to write an equation for the line of fit for the data. So let's start out by drawing the scatter plot. So we can see here we have all positive x and y values, so I'm going to help out with my graph here by not having anything but the first quadrant. Okay, and then I can go 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so we're going by ones here, and we want to be able to include all our data from 1 to 8 on the x-axis, and our y's go from 1 up to 14. All right, so now we want to graph those points. So I can plot the points, 1, 3, right, 2, 5, 3, 8, right there. Okay, this was 8. We can make sure we know where our points are here as we're graphing our scale on our axes. And we've got 4, 9, so 4, 9, 5, 11, and we've got 6, 12, and 8, comma 14. All right, so we can generally draw a line that goes through that data. We'll use a different color here so we distinguish it. So we're going to have a line that basically goes like this, right? So we've got about the same number of points above and below. We can see we've got about 3 points above, 3 below, maybe 1 right on it. And so that would be a line that best fits through that data. It's not exact, but it fits best. And now if we're going to write an equation that models this, to write an equation for this, we need to pick 2 points that are on the line. They don't have to be 2 of the dots we've drawn. I'd say this is a good one right here, 6, comma 12. And then we could look through and find some other point. It doesn't have to be here. We could do 2, comma, let's see, 1, 2, 3, 4, 5, 6. So 2, comma 6 looks like a point that would be on there. So let's write those 2 points out. So we have a point right there, 2, comma 6, and we have a point right there, 6, comma 12, and we could write an equation using those 2 points. We're going to need the slope. Just like always, that's where we should start. So my slope would be 12 minus 6 over 6 minus 2. Y minus y over x minus x. That gives me 6 over 4, which would be 3 over 2. And now I could use one of those points on my slope to write using point slope form. I'm going to use the point 2, comma 6. So we're going to take y minus 6 equals 3 over 2, x minus 2, point slope form. Now I'm going to have y minus 6 equals 3 over 2x, it's a minus, minus 3. And I can add 6 to both sides, and I would get y equals 3 over 2x plus 3. That would be the equation for my line of fit. Okay? And if we look at it, we could see I got a y-intercept of 3. This looks like it would have, that line drew, have about a y-intercept of 3. We can see if it looks like it makes sense. So that would be a line of fit that best fits through that data. It's not an exact line where all the points are on it, but that line best fits the data we had there. It fits through there, generally through the middle, and we pick 2 points, and we can write the equation for that line. All right, before we see some more lines of fit, how much does the moon weigh? Well, since the moon is in free fall in orbit, it doesn't actually weigh anything. So it has no weight, but it does have mass. It's about 7 times 10 to the 22nd kilograms. So 7 with 22 zeros, that'd be 70 sextillion kilograms. That's a pretty big number. And it is quite big, but it's 1% of the mass of the Earth, which is still pretty big. That's about the mass of the moon, even though it has no weight there in orbit. All right, now as we return from space, back to some lines of fit. All right, let's make a scatter plot here and write the equation for the line of fit. Then we're going to use that equation to estimate another value. So we're going to take another step beyond just writing the equation. All right, so let's graph these points. Draw my graph out here. We've got all positive x's, but I got a couple negative y's, so I'll draw something like this. My x values go 1, 2, 3, 4, 5, 6, 7, 8. We're going out to 8. Okay, my y values, I'm going to go by 2's. 2, 4, so negative 4. And I've got 2, 4, 6, 8, 10, 12, 14, 16. All right, so I should be able to fit everything on my grid here. That's 2, that's 3, this would be 6, and I'm counting by 2's on my y-axis. So let's plot these points. All right, so we're going to plot the point 1, comma, negative 4. That's right there. Then we're going to plot the point 2, comma, negative 1. 2, comma, negative 1, or we're going by 2, so 2, comma, negative 1 right there. Then 3, comma, 1, 3, comma, 1 right there. 6, comma, 8, so 6, comma, 8, be right around there. And then we've got 8, comma, 15, 8, comma, 15, right up there. Okay. And now if I want to draw a line that best fits through that, I can do my best to draw a line. If you get out a straight edge, it can help as well when you're drawing these lines. So let's see what we can do to get some points that maybe are on that line. So it looks like 2, negative 1. We'll use that as one of our points. And then I'm going to come up here and pick a point that looks like 7, comma, 11. 7, comma, 11. All right. So I'm going to use those as my 2 points. 2, comma, negative 1 and 7, comma, 11. Depending on how you draw the line, right, there's going to be some variation here. So not all of these are going to be exact. The line of fit is the best fit. And not everybody's drawing of the line of best fit and the points you pick are going to be exact, but they should be pretty close. All right, so now we're going to write the equation for this. So my slope, okay, is going to be 11 plus 1, so 11 minus negative 1 is 11 plus 1 over 7 minus 2. That's 12 over 5. Right? So now, when I go to write this equation, I'm going to get some fractions I'm going to have to work with. So I'm going to use the point 2 comma negative 1 to write my equation from here. So when I do that, I'm going to have y plus 1 equals 12 over 5, and then parentheses x minus 2. And when I distribute, I'm going to have y plus 1 equals 12 over 5x and minus 24 over 5 when I distribute the 12 over 5 times the negative 2. Now when I subtract 1 on both sides, subtracting 1, that's like subtracting 5 over 5. I'm going to have y equals 12 over 5x minus 29 over 5. So that would be my equation for the line of fit. Right? That's my line of best fit, and write the equation. And we're going to use that to estimate y when x equals 5. Right? So I wrote the equation for the line of fit. Now I want to say, what is the y value going to be when x equals 5? This is called interpolation. Right? When we're getting something that's inside of the data, we don't know what happened when x is 5, but we should expect it to be something in this range, somewhere in there. So we can use our equation now to say, okay, when I plug a 5 in for x, what about would the y value be? So let's do that. So I'm going to take my equation. I'm going to have y equals 12 over 5 times 5 minus 29 over 5. Right? I put a 5 in for the x. So that's going to be equals 12 minus 29 over 5. 12 is 60 over 5 minus 29 over 5. So it's going to be a y value of 31 over 5. So it would be my y value when x is 5, which is a little above 6. If I look on my graph, x value of 5, I come up here, and that would come across and be right just above 6. So that seems pretty realistic to where my point would be if I was on that graph, right? When I put an x value of 5, I'd have a y value of around 6, which, does that make sense in our table? Yeah, I think if I had 5 for the x, right, a y value of around 6 would make sense for the way that data is going. So again, that line of fit gives us an idea to estimate and approximate the best we can what the value of something would be that's not in our data. That's called interpolation. Extrapolation is when we look for something that's beyond the data. We're still going to use the same method, okay, just terminology. Extrapolation, we say what happens when x is 10. Well, x is 10 is outside of the data instead of something like 5, okay, or 6. It would be inside of the data we have. So you should pause the video, draw a scatter plot, draw your line of fit, see what equation you come up with, and then press play again, and I'll tell you what I came up with for mine. Okay, so you should have drawn a scatter plot and had a line that was generally going down with a negative correlation, because as the x increases here, the y's decrease. The equation that I got, and they're not going to be all exactly the same, I got y equals negative 18 over 7x plus 158 over 7. So you should have a negative slope. It's around, negative 2.5, something like that. So you could see if yours was at least close to that. Again, they're not going to be the same exactly. And then when I plug in x equals 10, I got y equals negative 22 over 7. So when x was 10, I got negative 22 over 7, around negative 3. Again, you should have something that's at least close to that. It's not going to be exact, right? So understand there's going to be some variation in these things, but you draw the scatter plot, draw the line you best fit through the points, have 2 points, and write an equation like with any other time you have 2 points. Find slope, and then get a y-intercept, and you've got an equation that you can use. Now let's see one last thing. The zero of a function is the x value when the whole function has a value of 0. That's why it's called the zero of a function. What x value makes the y value, or f of x, equal to 0? So in this situation, we have a youth softball participants equation. They can tell us how many people were participating every year since 1997. So we want to find the zero of the equation. We're going to put a 0 in for y, and then we're going to solve for x. Right? We want to find the x value when y is 0. So I can subtract the 1.435 on both sides, and then I can divide by negative 0.02, and we'll get that x is about 71.75, okay, or about 72. So that means 72 years after 1997, it was when there were 0 people participating in softball. So the zero of a function is the value plug in for x that gives you a y value of 0. It's essentially the y-intercept, right? The y value when x is 0.